What we want to do now is we want to look at functions that don't have a specific algebraic rule, or at least not a very nice one. This function f of x is actually a piecewise function that would have written out not one, not two, not three, but 4 different rules depending on which input value you chose. One of the reasons it's important to be able to work with these types of functions is that in AP Calculus, often to test your understanding of the concept, instead of giving you a function that has a familiar algebraic rule, they'll give you a function graph that can't be defined very easily by one, and ask you to apply the calculus concept to that function. So we should start practicing with this type of function now. Given this function f of x, if g of x is negative f of x, can we make the graph? Well, let's think about what that negative of f of x would do. Since it's applied to the function itself, it would multiply all the y's by -1. It would treat the x-axis as a mirror and reflect the graph of f of x across it. So each point on the graph of f of x should have the same x-coordinate, but the opposite of the y-coordinate. So let's pick out some important points there. Here's a point on f of x that appears to be at -3, -2. On g of x, that should be at -3, +2, right there. The end of that line segment is at the point -2, -1. On g of x, it should be at -2, +1. And if every point on that segment is connected by those two endpoints, I think we can do the similar thing here. We can understand that the signs of each of those functions would simply change. We can make our next line segment by going from 0, -5 to 0, +5. Like so. The third line segment in this function f of x goes from 0, -5 to 2, 3. The corresponding point on g of x should be 2, -3, right here. And the final line segment in f of x ends at 6, 2. We should end this graph at 6, -2. And there it is. Now, it's poorly drawn there. It wasn't the straightest line segments there, and that's okay as long as you indicate clearly what we're dealing with. What about h of x? What about f of -x? Now, the difference here is that that negative sign is applied to the x, the input itself, not the function. So technically, this is a division of all of the x's by -1. It's simply going to change the x-coordinate of each point. So the point on f of x that was at -3, -2 should be at 3, -2. We're going to reflect this across the y-axis. The point at -2, -1 should be at 2, -1. And the line segment should connect like this. The point at 0, -5 should still be there, since the opposite of 0 is 0. The next segment, which would have ended at 2, 3, should end at -2, 3. And the very last segment in f ending at 6, 2 should end at -6, 2. Okay, this one is for you to try. It's a different function f of x, notice. Why don't you see if you can make these sketches, give it a shot, and when you think you've got it sorted out, hit play and give yourself some feedback. If I want to find the graph of 2 times f of x, noticing that that 2 is happening to the function itself, that will simply multiply all of the y's by 2. It's going to stretch the graph out so that it's twice as long. Each point should be twice as far away from the x-axis as before. So the point at the very left end point of f of x at -5, 2, if I multiply the y-coordinate by 2, should now be at -5, 4. And the line segment part of f of x ending at -2, -1, if you multiply the y by 2, should be at -2, -2. You know, this little horizontal line segment here that ends originally at 0, -1, will end at 0, -2. And we had a point at 1, 0. And if I multiply the y by 2, I still am at 1, 0. And then the final segment I see here ends at 4, -3. Where is that going to end? Yeah, 4, -6. Something like this is what g of x should look like. Now the different thing here about h of x is that there's two things going on. We've got f of x minus 2 plus 3. So firstly, x minus 2 happening to the x is going to shift which direction? Yeah, it's right 2 units. And then adding 3 to the function itself will take us up 3. So what I want to do is I want to take each of the points on f of x, right 2, and up 3. So if I start at -5, 2, and go right 2, and up 3, I believe I'm at -3, 5. If I take the end of that first segment, which was at -2, -1, right 2, and up 3, I'm at 0, 2. If I take the point at 0, -1, right 2, and up 3, I'm at 2, 2. I see a point at 1, 0, right 2, up 3, puts me at 3, 3. And then for the point that was at 4, -3, right 2, and up 3, gets me to 6, 0. Should look something like that. How'd you do? Alright, this one's for you as well. Give it a shot. When you think you've got it worked out, hit play and we'll check it out. You know, there is something different about f of x here compared to what we've worked on previously in this video. Not all of the portions of this graph are linear. You've got a portion here that's almost like a semicircle. Another difference is that it's not what we call a continuous function. You couldn't draw this whole function from left to right without picking up your pencil and going to a new location. But those differences really don't make a big difference in how this is going to work out. You'll just need to consider some of those differences in making the sketch of the graph. So for g of x, we've got the opposite of f of x minus 1. The minus 1 applied to x is going to take our graph to the right 1. And then, multiplying the function itself by -1 will multiply the y's by -1. So we need to apply that to each of the key points in the graph to make a sketch of the function we're looking for, g of x. So if I look at the very left here, at the point at -5, 3. -5, 3. If I go right 1, I'm at -4, 3. If I multiply the y's by -1, I should finish at -4, -3. And if I take the end of that segment at -2, 0, if I go right 1, I'm at -1, 0. Multiplying the y-coordinate by -1 won't change the y value. It still puts me at -1, 0. So this whole line segment should look something like that. Now looking at this semicircle, it might be helpful to take like the end point here, kind of that point there, and then think about this open, not quite there point, to indicate that, you know, we've got the whole semicircle up to that very end point. So let's kind of work with those 3 points and see what happens. Of course, that first point we've already found, it's at -1, 0. If I take that point at the top of my semicircle at 0, 2, if I go right 1, I'm at 1, 2. If I change the sign of the y-coordinate, I finish at 1, negative 2. Now this open dot at 2, 0, if I go right 1, puts me at 3, 0. Multiplying y by negative 1 keeps me at 3, 0. And since that dot was open there, I should make it open here as well, too. Open dot. And all I've got is that semicircle, instead of going up, it's going to go down. We'll try to sketch that as best we can. Good. Now, this last kind of disconnected segment here starts at 2, negative 2. So if I go right 1, and then change the sign of the y's, I should be at 3, 2. With a filled-in dot, notice that's important. And then the point at 4, negative 3. Right 1 to 5, negative 3. Change the sign of the y to 5, 3. Something like that. What does, in h of x, multiplying the x by 2 do? It actually divides the x's by 2. Remember that anything that happens to the input itself affects the x values. So we want to take each of those same key points in f and divide the x by 2 only. So the point that was at at negative 5, 3, if you divide the x by 2, you get negative 2.5, right about there. The end of that segment was at negative 2, 0. If I divide the x by 2, I'm at negative 1, 0. That whole segment should look something like that. The point at 0, 2 that creates kind of a quarter of my circle, well, I guess half of my half a circle, won't move because the x is 0. But the open dot at the end of my half circle that was at 2, 0 is now at 1, 0. What's going to happen here is it won't really be a half a circle anymore. It would be a pinched in half a circle. The point, the filled in dot for the last segment at 2, negative 2 is now at 1, negative 2. And the end of the segment that was at 4, negative 3, half of 4 is 2, it's at 2, negative 3. And there should be a sketch of what h of x looks like.